All right, and now that we have a way of expressing the probability density of one image, we can express the probability density of any set of k images. And because the noise in each image is independent, it turns out that the probability density of all the k images put together is simply a product of the probability density of each image. And the probability density of each image is, of course, what we had on the previous slide. And this density, as I've written down, tells you the probability density of the k images, knowing their k projection directions and their k embedding parameters. But you can do the same thing when you have integrated out the projection directions and the embedding parameters. And again, the probability density of I1 through Ik turns out simply is a product of the probability density of each image. And so that's the final modeling step that we have for the image formation model, is that using the equations we have had previously on previous slides, we can simply write down these probability densities. And it's actually important to understand what this equation represents. So what this equation represents is actually an entire function, an entire probability density, where if you observe some images I1 through Ik, you can plug them into this equation, and this equation tells you how likely it is that those images will be observed when you have a structure S, when you have projection directions I1 through Ik and embedding parameters theta 1 to theta k. So it's the entire function, the entire probability density that's described by that equation. And the same for this. This tells you what is the probability density of actually observing I1 through Ik given the structure S. Okay, so that's all we need to know about the forward modeling part of CryoEM. In the next lecture, we're going to take that description of the forward model and then try to figure out how we can infer the structure S from this forward model given images I1 through Ik. Okay, thank you.